GCE Advanced Level, Chemistry Practical Series, Experiment number 18. Identification of the colors of complex ions formed in aqueous medium. Aim of this practical is to identify the colors of ions that are formed by the D block elements in the aqueous medium. As you may know, there are D block elements that are falling under the category of transition elements. These transition elements, specifically the transition elements, when they are forming aqueous solutions, or when their ions are forming aqueous solutions, they are going to be a colorful solution. So we are going to be identifying the colors that are formed by different transition element cations. So students, before we move any further, we have to identify what are D block elements and what are transition elements, and why some transition elements are actually producing colorful solutions in aqueous medium. So if you take a look at the definition of D block elements are elements that will have the highest energy electron, or the final electron, being filled to a D subshell. So if you take a look at the 3D elements are going to be going from scandium to zinc. So all of the elements in between scandium, including scandium and zinc, are referred to as 3D elements. However, not all 3D elements are transition elements. By definition, transition elements are elements that would contain incompletely filled d orbitals when they are present as an element or when they are present as an ion. So if you don't have incompletely filled d orbitals in either of those states, those elements, even if they are present in the 3D block, we will not consider them to be transition elements. Now, all of this information is present here in the introduction as well. Keep in mind that zinc is not considered as a transition element. One of the reasons why we don't consider zinc to be a transition element is that it does not contain any incompletely filled d orbitals. Even when it's present as an element, it contains a completely filled 3D subshell, and when it's present as an ion, zinc 2 plus ion, it does not contain any incompletely filled 3D subshells, because the 3D subshell in zinc is completely filled even when it's present as a zinc 2 plus ion. So zinc is not considered to be a transition element. Now let's take a look at the introduction. The characteristic features of compounds formed by the D block elements is that their aqueous solutions are colored. If the ions are formed by D block elements have a half-filled d orbitals, they are referred to as transition elements. Now, very important few pieces of information is communicated here. Now students, what are D block elements? D block elements are elements that have their highest energy electrons filled to a D subshell or D orbital. So whenever you have their highest energy electrons filled to, or the final electron being filled to a D subshell, then we categorize those kind of elements as D block elements. When you have at least one incompletely filled d orbital in an element, especially when they are present as an element or when they are forming ions, if they contain incompletely filled d subshells or d orbitals, we will consider them to be transition elements. So transition element definition and D block element definition are two different things. Not all D block elements are transition elements. Right, so when you are considering transition elements and D block elements, you have to keep in mind the difference between the two definitions. So transition element cations, if they contain incompletely filled d orbitals, will display a color in the aqueous solutions. The characteristic feature of transition metal ions is that they show colors in aqueous solutions, what I just mentioned a while ago. So transition metal cations are always going to be colorful, especially transition metal cations that contain incompletely filled d orbitals when they're forming ions. The reason why I mentioned that you need to have incompletely filled d orbitals to show a color is that when you have incompletely filled d orbitals, when they're forming ions, these ions are capable of absorbing energy or radiation from the visible light spectrum of the electromagnetic spectrum. So in this visible light region, when you absorb an energy, what happens is you can see a color that is emitted by the ion solution. So each of these different transition metal ions have their corresponding characteristic color. So today we are going to be observing what those corresponding colors are. So these ions absorb energy or absorb the selected wavelengths belonging to white light and show relevant colors at the excited state that they will go into. In considering 3D elements as zinc and scandium do not form ions having unpaired electrons. Their aqueous solutions are not colored. As I mentioned earlier, zinc is not going to be considered a transition element. Zinc is not considered a transition element because zinc does not contain any incompletely filled d orbitals. It does not form any ions with any incompletely filled d orbitals. So therefore, both in the element state of zinc as well as in its ion state, it will not form any incompletely filled d orbitals. So therefore, zinc is not a transition element. Zinc is in fact a d block element, but it is not a transition element. However, scandium is a transition element. But scandium, when it is forming its only ion, scandium 3 plus ion, it will not have any incompletely filled d orbitals. Its 3D subshell will be completely empty, so therefore it is not incompletely filled. So at this point, it is not going to be producing any solutions with a color. Let's move on to the next slide. So in this slide, you can see when it comes to zinc, we see when it comes to zinc, it is not considered a transition element. However, all the other elements in the 3D block or 3D elements, starting from scandium to copper, they are considered to be transition elements. But zinc is not a transition element. So if you want to find out the reason for it, you can see if you write the electronic configuration, we'll abbreviate the electronic configuration like this, and then you have 3D10 4s2. So at this point you can see when zinc is present as an element, it contains a completely filled 3D subshell. What about when zinc is forming a 2 plus ion? At that point, you will see again 3D10 4s0. So at this situation as well, you don't see any 3D subshells where they are incompletely filled. There won't be any unpaired electrons found in the 3D subshell because it is completely filled. So zinc is not going to be considered a transition element here. But at the same time, we spoke about scandium. Scandium is in fact a transition element. If you take scandium, we have its electronic configuration written like this. At this point, scandium is considered a 3D element. Why would it be considered a 3D element? Because you can see when scandium is present as an element before forming an ion, it contains an incompletely filled d orbital. Or in the 3D subshell, we have one electron in the entire 3D subshell, which makes the 3D subshell incompletely filled. So this qualifies scandium to be defined as a transition element. However, when you're talking about colors of the cations that they form, aqueous medium, scandium 3 plus ion solutions will be colorless. This is due to the fact that when you are forming scandium 3 plus, 3D and 4s subshells will hold no electrons. There will be no electrons present in the 3D subshell. So therefore, it is completely empty. When the 3D subshell is not containing any incompletely filled d orbitals, at that point, I will not be able to absorb energy from the visible light region of the electromagnetic spectrum. Therefore, they will not be able to show a color in the aqueous cation solutions. Now, let's move on to our experiment and talk about the equipment and the chemicals we'll be using for this practical. We'll be using these equipments, test tubes, glass rods, and measuring cylinders. The chemicals that we are going to be using are these: chromium chloride, manganese sulfate, iron chloride or ferric chloride, ferrous sulfate, cobalt nitrate, zinc sulfate, copper sulfate, nickel nitrate, and distilled water. So what is the procedure for this experiment? We are going to be weighing about 0.5 grams of above mentioned chemical compounds. So we mentioned a few chemical compounds in the previous slide. So we are going to measure about 0.5 grams or half a gram of those compounds, and we'll be adding them into separate test tubes and we'll be labeling them. Afterwards, we will add 10 cubic centimeters of distilled water to each of these test tubes, and we will dissolve the compounds well using a glass rod. So students, you measure half a gram of each of these compounds that we have in the lab. We will add them to a test tube, and using a glass rod and distilled water, we will be stirring and dissolving these solids in distilled water. And as these solids dissolve in distilled water, we are going to observe different colors for different cation solutions. And then we are going to record the colors of each of these solutions in a table. And students, we have already done this experiment and you might have already observed the colors of these solutions in the past as well. But let's take a look at the colors that you will be observing when it comes to different cation solutions. So when you are doing these practicals in the lab, some of these colors, such as manganese 2 plus ion solution color, will not be very clear to you. However, let's take a look at the colors that each of these cations are said to be forming. So chromium chloride. When you dissolve chromium chloride solid in water, it releases chromium 3 plus ions and chloride minus ions into the medium. Chloride minus ions do not have a color. So therefore, if you see a color at all in this solution, that is due to the chromium 3 plus ions. And when you dissolve chromium chloride in water, the color that you observe is going to be green. It's a green color solution that is going to be formed. When it comes to manganese sulfate, you're going to get Mn2 plus ions as well as sulfate ions. So Mn2 plus ions are going to have a color, however, sulfate ions will not have a color. Manganese 2 plus is having a color that is a pale pink color. The color intensity of this specific color is going to be extremely low at low concentrations of Mn2 plus or at moderate concentrations of Mn2 plus. You will not be observing this color very clearly even in the lab environment. It's going to appear somewhat colorless. If you have ever done a titration using potassium permanganate, where potassium permanganate is turning into Mn2 plus, we actually use potassium permanganate as a self-indicator. Also, at this point, we are going to turn potassium permanganate, which is purple in color, into a colorless solution. So we say the final solution that is formed is colorless or very pale pink. This pale pink color is due to the formation of Mn2 plus. However, the Mn2 plus ion solutions are not going to exhibit a very strong pale pink color. Due to the lack of intensity in this color, you're going to see it as a colorless solution. So observing this pale pink color would require really high concentrations of Mn2 plus ions being present in the medium. At moderate concentrations of Mn2 plus ions in the medium, you will observe the solution to be somewhat colorless. But keep in mind, the characteristic color of Mn2 plus aqueous ion solutions is pale pink. Then we turn to Fe2 plus, ferrous 2 plus ions or ferrous ions. Ferrous ion solutions can be obtained by taking ferrous sulfate. So we take ferrous sulfate. Sulfate ions, as I mentioned earlier, are going to be colorless, and we have Fe2 plus ions and sulfate ions released into the medium when you are dissolving it in aqueous solution. And Fe2 plus ions will be producing a pale green color solution. So the solution is going to be turning into a pale green color solution. And if you take ferric ions, Fe3 plus ions, so we can obtain Fe3 plus ions by taking ferric chloride. So chloride ions, as I mentioned earlier, will be colorless, and Fe3 plus ions will be the only species responsible for forming a color in the solution, and the solution's color will be yellow-brown. So Fe3 plus ions will be yellow-brown in color. When it comes to cobalt nitrate, when you dissolve cobalt nitrate in aqueous medium, cobalt 2 plus ions and nitrate ions will get dissociated, just like all the ions that we discussed earlier. So nitrate ions are again colorless. Nitrate ions do not have a color. So we observe a pink color in the solution when you're dissolving cobalt nitrate in an aqueous medium. So what is the species responsible for this color? The copper 2 plus ions would be producing a pink color solution. And when it comes to nickel, we take nickel sulfate. We know sulfate ions don't have a color, and nickel 2 plus ions will be responsible for producing a green color in nickel sulfate solution. So if you take nickel sulfate, dissolve it in water, the solution is going to turn green, and the green color is formed due to nickel 2 plus ions. Copper sulfate, I'm quite certain that most of you are very familiar with copper sulfate, right? So copper sulfate is going to be obtained as an anhydrous solid as well as a hydrated solid. anhydrous solid of copper sulfate is going to be white in color when they're present as a solid. And hydrated form of copper sulfate, CuSO4 5H2O. So this hydrated form of copper sulfate solid is going to appear pale blue in color or blue in color. So when you take in the lab environment, we normally have the hydrated form more commonly. So if you take a look at the copper sulfate you have in your lab, you would note that you have the hydrated form, because the copper sulfate that you have in the lab is going to be a pale blue color solid. So when you take this pale blue color solid and dissolve it in water, you form a pale blue color solution. And as you know, the sulfate ions are colorless. So the copper 2 plus ions that are present in the medium will be the ones responsible for producing this pale blue color in the solution. And finally, we move on to zinc sulfate. So zinc sulfate is a compound of a 3D element. Zinc is a 3D element. However, zinc is a transition element. So as we know, transition element cations usually produce colorful solutions, except for zinc 3 plus ion solutions. And at the same time, since zinc is not a transition element, when you have zinc 2 plus cation solutions formed, you don't see a color in the solution. They are going to be colorless. So when you take zinc sulfate, when you dissolve it in water, you will dissociate the compound into zinc 2 plus ions and sulfate ions, and both of these species are going to be colorless species. So therefore, the solution is going to be colorless. Now, students, we are moving on to the formula and structures of aqueous complexes that produce different colored solutions. Let's turn our attention first to copper, one of the more familiar elements for most students who are watching this video. So we obtained a copper 2 plus ion solution by dissolving copper sulfate in water. And as the sentence says, aqueous solutions are pale blue in color. If you take copper sulfate solid, dissolve it in a little bit of distilled water, you're going to obtain a pale blue color solution. So copper sulfate aqueous solutions are pale blue in color. And we know that there is copper 2 plus ions in the medium. They are the ones responsible for this pale blue color found in the medium. And we mentioned that in the previous parts of this theory part. Sulfate ions, of course, are going to be colorless. They will not show any color. Given below is the complex responsible for the pale blue color observed in copper 2 plus ion solutions. So as you can see, when copper 2 plus ions are present in the aqueous medium, water molecules can donate a lone pair of electrons towards copper 2 plus ions and form a coordination bond, or else it is also known as a dative covalent bond. So this bond can be formed between many d block elements, and therefore d block elements are known to form coordination compounds with different ligands. So water here is acting as a ligand and will be donating a lone pair of electrons towards the copper 2 plus ions and will form dative bonds, and the complex that is formed due to this is going to be CuH2O6. One copper 2 plus ion will form 6 coordination bonds with 6 water ligands and will form Cu H2O6 plus 2 complex ion. And this complex ion specifically is the reason for the blue color in the solution. Earlier on, we said copper 2 plus ions were responsible for the blue color in the solution. Yes, it is true, but very specifically, the complex that is producing this blue color is CuH2O6 2 plus. So this complex is blue in color. And we have to know how to name these kind of complexes. So IUPAC nomenclature tells us how to name these complexes, and we have learned about it. So if you take a look at the ligands first, we see there are 6 water ligands. So we will write the multiplier hexa, indicating that there are 6. Aqua indicates the presence of water ligands, and then since this is a positively charged ions, we can just straight away write the name of the element, copper, and the oxidation state of copper in this complex is +2. So hexa aqua copper 2 ions will be the name of this complex ion. Hexa aqua copper 2 ions. So let's observe the shape of this complex, as well as how to draw this complex. So the structure of hexa aqua copper 2 ions is given here. So hexa aqua copper 2 plus ions, you have the complex here. As you saw earlier, this had an overall charge of 2 plus, and so in the aqueous medium there are negatively charged ions such as sulfate ions. So when they are in the presence of each other, they can actually form this complex. So the complex copper ion will connect with the sulfate ion to form this coordination complex, and the name of that coordination complex would be hexa aqua copper 2, and then we have a sulfate ion. So we will indicate that after leaving a space, hexa aqua copper 2 space sulfate. And when you're writing the word sulfate, make sure to use an F and not PH. So sulfate has to be spelled out SULFATE. And then we have the structure of the copper complex that we have formed here. So each water molecule that we have here has donated a lone pair of electrons into the copper 2 plus ion. So if you take a look at water, we'll start with the copper 2 plus ion. So copper 2 plus ion is going to be present in the middle, and we are going to have water molecules. Water molecules normally have, especially on oxygen, you have a lone pair of electrons. Actually, we have 2 lone pairs. So one of these lone pairs can be donated to copper 2 plus ions to form a dative covalent bond. And when 6 water molecules, now they are referred to as water ligands, when 6 water ligands donate lone pair of electrons like so, you actually produce the complex or the structure that we have indicated here. So each of these water molecules that we have over here, if you want to separately identify them, we have these water molecules. They are forming dative covalent bonds with the copper 2 plus ion, and there are 6 water molecules around copper forming these kind of dative covalent bonds that lead to formation of CuH2O6 2 plus ion. And students, when you are forming this complex, you will see when you're forming this complex, the charge of copper is 2 plus. So the overall charge that is brought in by the copper is going to be plus 2. And there are 6 water ligands, right? So there are 6 water ligands. And each water ligand or water molecule has a charge of 0, or in other words, no charge at all. So there's not any charges, there are no charges brought in by water molecules. So therefore, when these water molecules are forming a complex in combination with copper 2 plus ions, the overall charge of the complex happens to be plus 2. That's why when you are writing the formula, or when you're indicating the structure of this complex, we see outside of these square brackets a plus 2 charge, because the overall charge of this complex is going to be plus 2. So you have to keep in mind, whenever you are forming a complex ion, you have to take a look at the charge of the main cation that is involved, as well as the charges of the ligands that are involved. So using these charges, you can figure out the overall charge of the complex ion. And then let's take a look at the shapes of these complexes, as well as the color. So we observe the color of this complex to be blue, but now let's take a look at the shape of these complexes. So we can see the shape of this complex is octahedral. We have the water molecules arranged in the following manner. So when it comes to the copper 2 plus ion, there will be 4 water molecules arranged in a single plane. And after arranging 4 water molecules in a single plane, there will be 2 other water molecules above and below that plane, altogether forming a tetrahedral structure like so. So this tetrahedral structure is the structure that is observed when it comes to hexa, aqua, copper 2 ions. And if you're talking about the covalent bonds, and if you're talking about the bonds, the nature of the bonds that are observed in this complex is going to be quite different. We don't have only simple covalent bonds. We have covalent bonds between oxygen and hydrogen. So you can see between oxygen and hydrogen there are covalent bonds. These are simple covalent bonds. Those are polar covalent bonds due to oxygen being extremely electronegative. However, between oxygen and copper, what you observe are dative covalent bonds, also referred to as coordination bonds. So there are dative covalent bonds between oxygen and copper. So what you observe here are 2 different types of bonds. First one is covalent bonds that are found in the water molecule, more precisely polar covalent bonds found in the water molecule. And then between the oxygen and the copper 2 plus ion, you find dative covalent bonds. Now let's move on to the next complex. The next complex we come across is nickel sulfate. So nickel sulfate, when dissolved in water, produced a green color solution. So aqueous solutions of nickel sulfate are going to be green in color, and sulfate ions are colorless, so therefore nickel 2 plus ions are the reason why you have a green color solution formed. So the main point, that is sulfate ions do not interfere with producing a color, is indicated here because sulfate ions are colorless. And given below are the complex ions responsible for the green color observed in the nickel 2 plus solution. So just like in copper 2 plus, there will be 6 water molecules forming coordinate bonds or coordination bonds or dative covalent bonds with the nickel 2 plus ion, and it will be forming nickel H2O6 2 plus complex ion. So water ligands, or more precisely, oxygen in the water ligand will donate a lone pair of electron towards nickel and will form a dative covalent bond. And 6 water ligands will donate lone pairs of electrons towards nickel to form nickel H2O6 2 plus complex ion. And the IUPAC name of this complex ion is, there are 6 water ligands, so we start with hexa to indicate 6. Aqua will be the name allocated for the water ligand. So hexa aqua is the number of water ligands that are present in the complex. And then we have nickel 2 ion. So nickel 2 ion, the 2 is indicating us the charge of the cation that we find in this complex ion. So the charge of the cation is 2. Hexa aqua nickel 2 ion. And this hexa aqua nickel 2 ion is the reason why we observe a green color in the solution. More specifically, hexa aqua nickel 2 ion is the green color species that we observe in this solution. So if you take a nickel chloride solution, we learned it is going to be, aqueous solutions are green in color. Now if you take a nickel sulfate solution and dissolve it in water, we will form the following complex. So as you know, the hexa aqua nickel 2 ion has an overall charge of +2. And in the medium, if you have sulfate ions, sulfate ions will come into contact with these 2 plus charged complex ions and will form a coordination compound that looks like this. And the name of this compound will be, so the complex ion, we already learned how to name the complex ion, and we can observe the name of the complex ion over here, and this was +2 in charge. And after that we have another anion attached to it. So this anion is sulfate, so you will indicate the name of the anion after leaving a small space. Hexa aqua nickel 2 sulfate. This is the name of this compound. So nickel 2 plus ions in solution are green in color, and obviously chloride ions in aqueous solutions will be colorless. So if you take nickel chloride solution also, we are going to be observing a green color solution. So if you have nickel chloride, you have the complex ion combined with chloride ions. So the complex ion is going to be nickel H2O 6 2 plus. And if you have chloride ions in the medium, you would need 2 chloride ions to combine with this 2 plus charged ion. So you would be forming this compound. Hexa aqua nickel 2 chloride. So this is the name, hexa aqua nickel 2 chloride will be the name of that coordination compound. So we have a few of the solutions that we are going to be observing the same color when it comes to nickel compound. So if you take nickel sulfate aqueous solution, you will have a green color solution. So the compound that we have here in this solution is going to be hexaqua nickel 2 sulfate. And over here we have again the same nickel 2 plus ions forming a green color solution. So in each of these solutions, the green color is due to formation of hexaqua nickel 2 ion. Hexaqua nickel 2 ion is the responsible species for the green color in all three of these situations. But the compounds that they form is hexaqua nickel 2 sulfate. Over here, when it comes to nickel sulfate solution, when it comes to nickel nitrate solution, hexaqua nickel 2 nitrate. And finally, we have a nickel chloride solution, which is hexaqua nickel 2 chloride. So when 6 water ligands are connected to the nickel 2 plus ion through dative covalent bonds, the shape of this complex that they form, just like in copper 2 plus ion complexes, it's going to be octahedral. So the shape of this complex would be octahedral. And if you are observing the nature of bonds, there will be covalent bonds in the water molecule. Polar covalent bonds, more precisely, will be observed in water molecules. These are all polar covalent bonds that are highlighted over here. And the dative bonds are observed between oxygen and the nickel 2 plus ions. So when oxygen is donating a lone pair of electrons to nickel 2 plus, what you form there is going to be a dative covalent bond. Now we move on to chromium 3 plus ions. So if you take chromium chloride, CrCl3, 3 chloride ions are in contact with the chromium ion. So the charge of chromium ion should be 3 plus, because 3 chloride ions bring in 3 negative charges. To balance that out, the charge of chromium would have been 3 plus. So aqueous solutions of chromium chloride are also green in color, just like nickel. This green color is produced due to the presence of chromium 3 plus ions in the medium. Chromium 3 plus ions in the medium will be the reason why you observe a green color solution when it comes to chromium chloride. As we all know, chloride ions are colorless, so they do not interfere with the green color that is produced due to the chromium 3 plus ions. And the complex that is actually responsible for the green color solution that is formed are these. Actually, there are 2 complexes that are responsible for the green color that is observed in a chromium 3 plus aqueous ion solution or chromium chloride solution. Because when you are introducing a chromium chloride solution to water, these are the possible complexes that can get formed that are green in color. So the first one, you have 1 chromium ion forming dative bonds with a chloride ion and 5 water ligands. Chloride ions and water ligands, if you take oxygens in the water molecule, contain lone pairs of electrons. So these lone pairs can be donated to a cation, especially a 3D or D block element cation, because they have incompletely filled d orbitals that can receive these lone pairs. So when they are donated to a cation, they will be forming dative covalent bond between those cations. And then we have, in this situation, we have a chloride ion. So chloride ions, if I indicate the electrons around the chloride ion, we can see there are overall 8 electrons around chloride, which makes chloride ion also an electron-rich species, which can donate a lone pair of electrons towards a cation. So what has happened here is that chromium has formed coordination bonds with, or dative covalent bonds with, one chloride ion and 5 water ligands, forming a green color complex. And the name of that complex is, now there are 5 water ligands. When you are naming a complex, keep in mind, students, you have to keep this in mind very clearly. Whenever you are naming a complex, you have to remember the names of these ligands. Water is referred to as aqua. And what about chlorine? They are referred to as chlorido. And when you're writing the name of these kind of complexes, you have to indicate the ligands also in a specific order. You have to write them in a specific order. So the names of the ligands will be written in alphabetical order. So aqua, A comes before C. So when you are writing the ligand names, aqua comes before chlorido. So you can see over here the name of the very first compound that we come across, or very first complex we came across, was penta, because there are 5 water ligands here, and then aqua, chlorido, chromium 3 ion. So penta aqua refers to the 5 water ligands that are found here, and chlorido referred to the chloride ligand that we find in this complex, and we have chromium 3 plus ions in this complex, and we know the oxidation state is 3 plus, so we have to indicate that in Roman numerals here, and you leave a blank or you leave a space and write the word ion, because this is overall having a 2 plus charge, so therefore it's going to be referred to as a ion. So this entire complex's name is going to be penta aqua chlorido chromium 3 ions. If you turn to the second complex, you have 2 chloride ligands donating lone pairs to form 2 dative bonds between chromium 3 plus ion and chloride ions. And the number of water ligands have gone down to 4. Earlier it was 5. So now the name would be, again, still the alphabetical order doesn't change. We have water ligands and chloride ligands. So water ligands are referred to as aqua, chloride ligands will be named chlorido. So aqua comes before chlorido always. And the prefixes that go before aqua to indicate how many times we find this ligand in the complex are not taken into consideration when you are arranging the name according to the alphabetical order. So prefixes like tetra or penta or di, tri will not be considered when it comes to organizing the ligand names according to the alphabetical order. We only take a look at the name of the ligand and what letters it is starting with. So it is, the name of it is going to be tetra aqua, aqua stands for water, and there are 2 chloride ligands, so we have di, tetra aqua, di, chlorido, chromium 3 ions. So tetra aqua stands for 4 water ligands, dichloride stands for the 2 chloride ligands, and then we have the chromium in 3 plus charge state. So we write tetra aqua dichlorido, chromium 3 ions. So the same names are given here, but if you observe very clearly, we used a chromium chloride solution. So when you take chromium chloride in a medium or in an aqueous medium of chromium chloride, you will have chromium 3 plus ions, chloride ions, as well as enough and more H2O. So once you form these complexes, such as the complexes that you came across earlier, chromium, penta aqua chromium 3 ions, overall charge of this complex ion is going to be +2. So when these complex ions are present in this medium, you have enough and more chloride ions that it can connect with to form this compound. So now we have a coordination compound with this formula. So each of these complex ions will connect with 2 chloride ions. So it will neutralize the overall charge that we find here. So what is the name of this formula? Penta aqua chloridochromium 3 was the name of the ion or cation in this situation, and then the anion found there is chloride. So penta aqua chromium 3 chloride. When it comes to the second one, it is going to be tetra aqua dichloridochromium 3, which is the cation, and again the anion would be chloride because we have enough and more chloride ions in the medium to act as the anion. So therefore, this is how you would actually write the name of the coordinate compounds found here. And the shape, again, like I mentioned earlier, is going to be octahedral. When it comes to the previous two examples as well, we saw when you had 6 ligands arranged around a central cation, the shape of that entire complex was octahedral. Now chromium complexes are no different to that. You will see the shape of this chromium complex is also going to be octahedral. The color, of course, we observed earlier on, but we'll remind you again, the color of this complex is going to be green in color. And you can see the chloride ligand that is present over here. Now, it's not all water ligands around the chromium 3 plus ions. In this case, we have a single chloride ligand when it comes to penta aqua chloride or chromium 3 ions. And there will be covalent bonds observed between oxygen and hydrogen, and then between oxygen and chromium you're going to have coordination bonds, and at the same time there's going to be a coordination bond formed between chlorine and chromium ions as well, because chlorine is also a ligand. So you have a coordination bond formed between chlorine or chloride ions and chromium ions as well. So in the next complex as well, the overall shape of this complex is also going to be octahedral. The color is green, and in this case we observe the presence of 2 chloride ligands, right? And students, observe the overall charge of this complex. Now let's take a look at why this plus charge is there. So if you take a look at the complex formula again, you have chromium, we have 2 chlorines, and you have 4 water molecules, H2O, and the overall charge that they have indicated is +1. Why might that be? Now chromium over here has a charge of +3. Each chloride ion has 1 minus charge, but there are 2 chlorines, of course. That means there's 2 negative charges. When it comes to water, do we have a charge? No. So you have +3 charge and and 2 minus charge coming in from chlorides. So the overall charge, when these 2 charges balances itself out, is going to be +1. So this +1 charge is the charge observed over here. So whenever you have a complex ion with a few different ligands, with few different charges, you have to calculate the overall charge of the complex. So the overall charge of this particular complex is going to be +1, and that is due to the reason that I explained earlier. And apart from that, we can see that there are covalent bonds present between the oxygen and hydrogen water molecules, and dative covalent bonds observed between chloride ions and chromium 3 plus ions, as well as oxygen atoms in the water molecules and chromium 3 plus ions. So all of these bonds that we observe are dative covalent bonds. Now let's move on to the next slide. What happens if sulfate ligands are forming a dative covalent bond with chromium 3 plus ions? So when sulfate ligands, as you can see over here, form a dative covalent bond with the chromium 3 plus ion, you form this complex, one chromium 3 plus ion with one sulfate ligand and 5 water molecules. This complex ion will also be green in color. You will observe a green color for this specific complex ion as well, and it is going to be octahedral and the color is green. So you will observe the same type of bonds. There will be just covalent bonds observed between oxygen and sulfur when it comes to the sulfate ion. When it comes to water molecule, again between oxygen and hydrogen, you will observe covalent bonds. But between the oxygen atoms of sulfate as well as oxygen, between these oxygen atoms and the chromium 3 plus ion, what we are going to observe is coordination bonds or dative covalent bonds. So these are the two types of bonds that you observe here in this complex as well. So all of the complexes we have spoken about so far, we observed these two bonds, covalent bonds. Specifically, if you are talking about water, we observed polar covalent bonds between oxygen and hydrogen atoms in the water molecule. But when you're taking the ligands and the cation, between the ligands and the cations, the type of bond that we observed was coordination bonds, or in other words, dative covalent bonds. With that, we move on to manganese. Now, manganese sulfate is going to be a light pink color solution. I mentioned earlier, light pink color will not be observed very easily in the lab environment unless and otherwise you have an extremely high concentration of Mn2 plus ions in the aqueous medium. What you observe is a near colorless solution. It's a near colorless solution. But the color of Mn2 plus ions are going to be light pink. And sulfate ions are colorless. We are missing a minus sign here. So sulfate ions are colorless. And the complex that is responsible for this light pink color is given here, where manganese 2 plus ions form 6 coordination bonds or 6 dative covalent bonds with 6 water ligands. So these complexes will produce this pink color solution, hexa aqua manganese 2 ion, hexa aqua manganese 2 ion. So this is the structure of the ion, students. So you can see manganese 2 plus ion is in the middle. There will be 6 water ligands forming dative covalent bonds with the manganese, forming an octahedral shape for the complex ion. As water molecules are neutral in charge, the overall charge of the complex is going to be the same as Mn2 plus ion. So the overall complex is going to be +2 in charge. And we observe the same 2 different types of bonds that we observed earlier as well in all the other coordination compounds. such as dative covalent bonds as well as polar covalent bonds between oxygen and hydrogen in water molecules. So water molecules have polar covalent bonds, and between the ligand and the central cation we observe dative covalent bonds. And the names of these compounds. So when it comes to the ion that is formed, we'll first of all talk about the ion's name. If you use manganese sulfate, you first of all form this ion Mn H2O 6 2 plus complex ion. So you have 6 water molecules. So we start with hexa aqua, indicating the 6 water ligands, and then you have manganese in its +2 oxidation state or with a charge of +2. Hexa aqua manganese 2 ions are these ions. So this particular ion is referred to as hexa aqua manganese 2 ions. Then if you use manganese sulfate in the medium, you will have enough and more sulfate ions. So the sulfate ions will come into contact with these hexa aqua manganese 2 complex ions, and when they join, they will form this compound which is named hexa aqua manganese 2. After leaving a space, you will write sulfate. Hexa aqua manganese 2 sulfate. If by any chance, if you use, instead of using manganese sulfate, if you use manganese chloride and form a pink color solution, the coordination compound that is formed is hexa aqua manganese 2 chloride, because at that point the negatively charged ion that is found in the medium is not sulfate, it is going to be chloride. Why? Because we used manganese chloride. If you use manganese chloride to obtain a pink color manganese 2 plus ion solution, the entire coordination compounds formula can be written like this, because you will form hexa aqua manganese 2 ions, this ion that we have written over here, and in the medium you will have negatively charged ions, and the negatively charged ions that you find in the medium of a manganese chloride solution would be chloride ions. If you use manganese chloride, that is, when you use manganese chloride, the negatively charged ions that you find in the medium would be chloride ions. So instead of sulfate, you will be having 2 chlorides connecting to this complex ion of manganese, and will form hexa aqua manganese 2 chloride solutions. And that will also be the same color, very light pink color solutions will be formed. Right, now we are moving on to cobalt. So cobalt nitrate aqueous solutions are going to be pink in color, and nitrate ions are colorless solutions. So what is the reason for this pink color? It will be cobalt 2 plus ions. So the cobalt 2 plus ions are the reason for this color that we find in cobalt 2 plus aqueous solutions. And if you take a look at the complex ions responsible for this color, we have this complex where cobalt is forming 6 coordination bonds with 6 water molecules, like in all previous situations, and we are forming a pink color solution due to the presence of hexa aqua cobalt 2 complex, right? So you can see cobalt 2 plus ion with 6 water ligands, and the shape of this hexa aqua cobalt 2 complex is going to be octahedral, and the color is pink, and the nature of the bonds, just like in all other previous situations, would be you will have polar covalent bonds in the water molecules. So water molecule is made with oxygen and hydrogen, and the bond between oxygen and hydrogen will be polar covalent bonds, and between the water ligand and the chromium ion, between the ligand and the central cation, there will always be dative covalent bonds. So those are the two different types of bonds we observe here. So the names of these ions are given here. The IUPAC name of the complex ion that is formed with water ligands when it comes to cobalt is hexa-aqua cobalt 2 ion. So we can observe the 2 plus charge of this complex ion. So therefore cobalt is present in its plus 2 oxidation state, or cobalt is 2 plus in charge. So the name of the ion is hexa-aqua cobalt 2 ion. When it comes to taking a cobalt nitrate solution, alongside this plus 2 ion, you have nitrate ions. Alongside the plus 2 ions, you will have NO3 minus ions, nitrate ions. So nitrate ions then will come into contact with this positively charged cation, complex cation, and then they will join together to form this compound hexa-aqua cobalt 2 nitrate. If you use cobalt chloride solution, the resultant compound would be hexa-aqua cobalt 2 chloride. So depending on what type of anion is present in the medium, so when we use cobalt nitrate solid and dissolve it in water, the only anion present in water at that point would be nitrate anions. So with the complex cation, nitrate anion will come into contact and will form hexa-aqua cobalt 2 nitrate. When it comes to using cobalt chloride, and when you dissolve cobalt chloride in water, the only anion except for OH minus ions that are present in water is going to be chloride ions. So chloride ions will come into contact with hexa-aqua cobalt 2 ions, which is the complex cation. So complex cation will come into contact with the negatively charged chloride anion and will form hexa-aqua cobalt 2 chloride. And all of these complexes or coordination compounds will be pink in color. Now we move on to iron 2 plus ions. So to obtain iron 2 plus ions into a medium, we will be using a ferrous sulfate solid, and you will dissolve ferrous sulfate in water, and the resultant solution will be green in color. And as we know, sulfate is colorless, so the color is mainly brought in due to the Fe2 plus ions introduced into the medium. So the responsible species for this green color in the solution is hexa-aqua iron 2 complex ion. So we can see when 6 water molecules form dative covalent bonds with Fe2 plus ions, they form a complex ion, hexa-aqua iron 2 ions, which will be green in color. Structure of the iron 2 complex is given here, where 6 water molecules are forming coordination bonds with Fe2 plus, and the shape of this complex ion is going to be octahedral. Our color is light green, and we do observe the same 2 different types of bonds, the covalent bonds between water molecules and dative covalent bonds between the cation and the ligands. And the name of the complex ion is hexa-aqua iron 2 ion. So the 2 plus charge of Fe2 plus ions that are present here is the reason for us to indicate in Roman numerals 2 in the name of this complex ion. Hexa-aqua refers to the 6 water molecules, and then we have the name of the cation ion, and the charge of the cation plus 2 is indicated by the Roman numeral 2, and then you leave a space and write ion. The overall name would be hexa-aqua iron 2 ion. And there are few different names of the complex coordination compounds that we form over here. When you take Fe sulfate or iron sulfate or ferrous sulfate, the final complex or coordination compound that is formed is this. But if you use iron chloride, you will get to this. If you use iron nitrate, FeNO3 twice, this is the coordination compound that you will be observing. So when you are using different solids to obtain a solution of Fe2 plus ions, the final coordination compounds that are formed are these. But keep in mind, they all contain the same complex cation, which is 1 Fe2 plus ion forming 6 coordination bonds with 6 water ligands and form hexaaqua iron 2 ion. Depending on what solid that you use. If you use sulfate solid, an ion that you have abundantly in the medium would be SO4 minus. When it comes to using iron sulfate or ferrous sulfate, the anion that is found more abundantly in the medium is going to be sulfate ions. So then sulfate ions will come into contact with hexaqua iron 2 complex ion and will form hexaqua iron 2 sulfate coordination compound. And if you use ferrous chloride, chloride ions will be the more abundantly present anion in the medium. So then chloride ions will bind to the complex cation to form hexaqua iron 2 chloride. And if you use nitrate or iron nitrate solution or ferrous nitrate solution, nitrate ions will be the more abundantly found anion in the medium. So with that, they will form hexaqua iron 2 nitrate coordination compound. So these are the colors of different coordination compounds that we can form with Fe2 plus ions. However, at the heart of each of these coordination compounds, the reason why we observe a green color in the solution is due to this complex ion, hexaqua iron 2 ion. If you take Fe3 plus ions, however, the color is not pale green. Fe2 plus ion solutions form hexaqua iron 2 ions, which is pale green in color. But Fe3 plus ions, they are not going to be green in color. They are yellowish brown or yellow brown. Normally, we refer to it as yellowish brown color solutions will be formed. So whenever you have Fe3 plus ions, we actually form a yellowish brown color solution. Most often, if you leave an Fe2 plus ion solution exposed to atmospheric oxygen, there will be an oxidation taking place, and these green color solutions later on will turn into a brown color solution. This will happen gradually, but this brown color solution is a result of forming Fe3 plus ions starting from Fe2 plus ions. So now if you are observing Fe3 plus ions, Fe3 plus ion solutions are going to be yellow brown in color. That is due to the presence of this cation. And if you take nitrates, they are colorless. So if you take ferric nitrate, dissolve it in water, the ions that you have in the solution that are responsible for that yellowish brown solution is going to be Fe3 plus. Fe3 plus solutions are yellowish brown in color. However, apart from that, you would notice the ferric ion solutions at room temperature are going to be acidic. If you have a higher concentration of Fe3 plus ion solutions in aqueous medium, it is going to be considerably quite acidic. What is the reason for this particular ion solution to be acidic? So the reason for that is explained here. Fe3 plus ions, when they are present in water, they will come into contact with 6 water ligands like any other complex ion that we discussed in the previous parts, and will form hexa-aqua 3 complex. So what we can see here is that complex hexa-aqua ion 3 ions. So these complex ions are formed by having one Fe3 plus ion connected to 6 water ligands. However, due to the high charge of Fe3 plus, they can deprotonate water molecules that are attached to it, or the water ligands can be deprotonated. H plus will be released due to this deprotonation, and therefore a water molecule that is connected to Fe3 plus can lose one of its H pluses or hydrogen atoms as H plus and will turn into an OH minus ion or hydroxo ligand. So because of that, H plus will be released into the medium. So this is the equilibrium that is there. A water molecule will undergo deprotonation and H plus will be liberated from that water molecule. So this liberated H plus will contribute to increasing the acidity of the aqueous medium. So this equilibrium is going to be having equilibrium position somewhat shifted towards the right hand side. And the second step also can happen where more than one water molecule undergoes deprotonation. As you can see over here, now there's already an OH group, but from the remaining 5 water molecules, one H plus can be liberated to form FeOH twice, H2O 4 times. And at this point, the overall charge of the complex ion that is formed would be +1. So students, now you might have noticed the reason for ferric ion solutions to be acidic, right? Due to these two equilibrium reactions, you would see H plus being released into the medium by deprotonation of the water ligands that are attached to Fe3 plus ions. And the overall charge of the complexes that they form will change accordingly. So if you take a look at the OH minus ion, there's going to be a -1 charge, and Fe or ferric ions have +3 charge. So the overall charge when you add them together would be +2. And in the second situation, the final product that they have formed has a complex ion with a charge of +1. So for the reason for that would be the ion over here, or ferric ions that we find over here will be +3 in charge, but there are 2 hydroxide ions. Each hydroxide is 1 minus in charge. When you have 2 of them, it will be 2 minuses. So therefore, when you add them together, the overall charge that is going to be remaining is +1. So this is the reason for only one positive charge to be outside of the complex's formula. So you have to understand by now how to identify the complex ion's charge or overall charge of a complex ion, as well as how ferric solutions are acidic in nature. And now let's move on to naming these complexes. Right, so both of these complexes are going to be yellowish brown in color. Regardless of them being acidic, it is going to be yellowish brown in color, and at the same time we are forming 2 different compounds, coordination compounds here, but still you're going to have the same yellowish brown color. So if you take a look at the very first compound, we have one hydroxide group and 5 water ligands. So when naming these compounds, when it comes to the hydroxide ions, their names are written as hydroxido, and water ligands are referred to as aqua. So A in English alphabet comes before H. So when you are arranging these names of the ligands in the alphabetical order, it's going to be aqua first and then hydroxo. So we will write the number of aqua ligands or water ligands first by writing penta aqua. Penta aqua indicates the presence of 5 water ligands, and then we have hydroxo or hydroxido. Right? Hydroxido indicates the presence of a single hydroxide ligand, and we have the name of the cation along with its charge, iron 3. And then since this entire complex ion is present as ion, since it is not neutral, we have to indicate the word ion. So in this case, the ion, ION, refers to forming something or a species, chemical species with a charge. If it was not having a charge, then it will be a neutral complex. What we see here is a complex with a charge, so we have to indicate that it is as such by writing the word ion. And the color of this will be brown. So again, to recap, the name of this particular complex is penta aqua hydroxido iron 3 ion. And in the second situation, we can see that 2 hydroxide ions are present alongside 4 water ligands when it comes to the second complex ion we see here. So this complex ion will be named in the same manner as we did earlier, but we have to make a small adjustment because the number of water ligands and the hydroxide ligands are now different. So we have 4 water ligands. We will be starting with tetra aqua to indicate the 4 water ligands, and there are 2 hydroxide ligands now, so therefore we'll call them dihydroxido, and then the name of the cation, iron 3 ion. Earlier it was penta aqua hydroxido iron 3 ion, but now since we have 4 water ligands and 2 hydroxide ligands, it is going to be tetra aqua dihydroxido iron 3 ion. And this is also going to be a yellowish brown solution. Let's move on to our next slide. So depends on what we use, depends on the solution that we use to form this yellow brown solution. We will obtain different ion complexes. So if you use iron sulfate or ferric sulfate, the anion that will combine with the iron 3 complex will be sulfate. So in general, we can actually write it as iron 3 sulfate. So iron 3 sulfate solutions are yellowish brown in color, and iron 3 nitrate solutions are also yellowish brown in color. But just like in the previous situations, you have to keep in mind, so if you have formed penta hydroxido iron 3 ions, and this is a cation, and if you have sulfate ions in the medium, sulfate ions will combine with this cation and will form penta aqua hydroxido iron 3 sulfate. If you use ferric nitrate to form a solution, then the resultant iron 3 complex would be penta aqua hydroxido iron 3 nitrate. So since there can be 2 ion complexes, we can simply summarize it and write iron 3 sulfate and iron 3 nitrate. And now we come across zinc sulfate. Zinc sulfate aqueous solutions are going to be colorless. Now, aqueous solutions are also colorless of zinc 2 plus ions. Now, these zinc 2 plus ions or zinc sulfate being colorless is due to zinc not being a transition metal at all. It doesn't contain any 3D incompletely filled 3D orbitals. So therefore, it is not capable of absorbing wavelengths from the visible light region of the electromagnetic spectrum and then producing a color. So zinc 2 plus ion solutions are colorless, sulfate ions are colorless, and the complex ion zinc 2 plus forms is also colorless. The complex ion that zinc 2 plus forms is hexaqueous zinc 2 ions, and that is colorless. Right, so hexa aqua zinc 2 ion. So just like in the previous situations, zinc 2 plus cation will form 6 coordination bonds with 6 water ligands and will form a complex ion, hexaqua zinc 2 ion, which is going to have no color at all, so the solution will appear colorless. In like in the previous situations, it is going to be octahedral shaped, this complex, and it's colorless. And we are going to be observing the same types of bonds. We are going to observe covalent bonds between water molecules, oxygen and hydrogen atoms, and we are going to observe dative covalent bonds between the ligand and the central cation. And if you use zinc sulfate to produce zinc 2 plus ion solution, the resultant coordination compound would be hexaqueous zinc sulfate. The formula is given here. And if you use zinc chloride, the resultant coordination compound would be hexaqueous zinc chloride. Hexaqueous zinc 2 chloride. And finally, we move on to scandium. If you use scandium chloride and prepare a solution, aqueous solution, it's going to be colorless. As we know, chloride ions are also colorless. So at the same time, there's no color observed in scandium 3 plus ions as well. Why? Because we learned when you take scandium 3 plus ions, and if you take a look at the electronic configuration, you would note it's going to be having no incompletely filled d orbitals. It will not contain any incompletely filled d orbitals. So when you don't have any incompletely filled d orbitals, it is not going to be able to absorb visible light energy or wavelengths from the visible light spectrum of the electromagnetic spectrum. So therefore, it will not be able to produce any colors in aqueous medium. So scandium 3 plus aqueous ion solutions will be colorless. So this is going to be colorless. So what is the name of this complex? So the name of this complex is going to be hexaaqua scandium 2 ions. Hexaaqua stands for 6 water ligands. Then we have the name of the cation scandium and the charge of the cation 2. Actually, the charge of the cation is 3. Hexaaqua scandium 3 ions, because scandium forms 3 plus ions. Hexaaqua scandium 3 ions. Now, this is the structure of the coordination compound that is formed. So in this complex ion, you can see there are 6 water ligands forming dative covalent bonds with the scandium 3 plus ions. As always, the shape of this type of complex ion is going to be octahedral, and the color is going to be colorless. and you will find the same two different types of bonds. Covalent bonds between the oxygen and the hydrogen atoms in the water molecules, as well as dative covalent bonds present between the water ligands and the scandium 2 plus ions. Now let's move on to our next slide. Students, in this slide, what you are observing is a comparison between two elements. So for this comparison, we have chosen two elements. One is referred to as a transition element found in the 3D elements, and the other one is zinc, which is not a transition element but still found in the 3D elements. So copper 2 plus ions, which is a transition element, are going to produce colorful solutions in aqueous medium. However, zinc, which is a non-transition element, their ion solutions, zinc 2 plus ion solutions, are colorless. In this slide, we are going to be focusing on why zinc 2 plus ions are not going to produce a color and why copper 2 plus ions are going to produce a color. If you write the electronic configuration of zinc, you will see it having electronic configuration ending with 4s2 3d10. Now some of the students would actually write this electronic configuration as 3d10 and 4s2, which is absolutely correct. Right? You can use both of these forms. It's not incorrect to use 3d10 4s2. And at the same time, this format actually indicates that the furthest subshell away from the nucleus of zinc is going to be 4s. So when you're removing an electron from zinc, the very first electrons that are going to be removed from zinc are going to be from the subshells that are furthest away from the nucleus. And 4s happens to be the subshell that is furthest away from the nucleus. So therefore, when you remove 4s2 electrons to form zinc 2 plus ion, the resultant electronic configuration would be this. 3p6, 3d10 would be the electronic configuration of zinc 2 plus ions. And one very special observation to be made over here is that when it comes to zinc 2 plus ions, it does not contain any incompletely filled 3d orbitals in this 3d subshell. So this is the entire 3d subshell. In each of its orbitals, you don't find any incompletely filled d orbitals. And then we are going to be observing copper 2 plus. Now copper 2 plus, before we observe copper 2 plus, let's take a look at copper elements electronic configuration, and you can see again we have electronic configuration ending in 4s1 3d10. So this is a special electronic configuration. Normally it is always 4s2 that is filled and then 3d. In this case, we can see one of the electrons are now going back into 3d, completing the 3d orbital. So 3d10 4s1 is also the correct format of writing this electron configuration. If you have written it like this, you don't have to worry, that is correct. So once you remove two electrons, the very first electron that you're removing is going to be the 4s electron that is found in copper. And after that, when you're removing the second electron, the electron configuration of copper 2 plus ions due to removal of two electrons would be 3p6 3d9. Now at this point, you can observe that the 3d subshell of copper contains one incompletely filled d orbital. So by definition, if an element in the d block forms ions, or when they're present as ions, or when they're present as elements, if they have incompletely filled d orbitals, they are referred to as transition elements. So copper by definition is a transition element. And then we jump into the reason why zinc 2 plus ions are not producing a color. They write zinc 2 plus ions do not contain any incompletely filled d orbitals. Copper 2 plus ions contain incompletely filled d orbitals. Due to copper 2 plus ions solutions, due to that, the copper 2 plus ion solutions will be colorful. So having incompletely filled d orbitals is very important. So when you have incompletely filled d orbitals, it actually allows for transition or dd transitions where electrons absorb energy from the visible light region of the electromagnetic spectrum, and then it will produce a corresponding color. So what that means is, when you have incompletely filled d orbitals in an ion, that allows for absorbance of energy. It allows for absorbance of energy from the visible light region. So otherwise, it allows for the 3D electrons to be excited by absorbing energy from the visible light region. If you have completely filled d orbitals, there's nowhere these electrons can be excited to, because all of the orbitals are completely filled. So at this point, they will not be absorbing energy from the visible light region. However, if you have at least one incompletely filled d orbital, there can be energy absorbed from the visible light region to excite electrons to a higher excited energy state. So because of this, there will be some form of color produced through absorbing energy from the visible light region. So as we do not go into detail about DD transitions in advanced level, we will not look into that topic here. However, you have to develop an understanding as to why transition element ions that contains incompletely filled d orbitals produces a color. And to summarize, the main reason is that when you have incompletely filled d orbitals in an ion, that allows for those electrons to be excited by absorbing energy from the visible light region of the electromagnetic spectrum. And due to absorbing energy from the visible light region, or in other words, white light, when you absorb wavelengths from the white light, or when you absorb energy from the visible light region, this will result in producing a color in those ion solutions. So therefore, this detail is summarized here. Due to having incompletely filled d orbitals in copper 2 plus ions, it can absorb energy from the visible light region of the electromagnetic spectrum. This results in copper 2 plus ion solutions appearing blue in color. So at the exam, if they ask you why transition metal ions that contain incompletely filled d orbitals are colorful, your answer should be, when incompletely filled d orbitals are there, they are capable of absorbing wavelengths from white light, or they are capable of absorbing energy from the visible light region of the electromagnetic spectrum and producing a color. So this is the reason why aqueous ions of transition metal cations are colorful. So now let's refresh our memory about the colors of few different ions. Now scandium is a bit of a special scenario because scandium is a transition element. However, scandium 3 plus ions will not have any incompletely filled d orbitals in it, so therefore it produces a colorless solution. And zinc is not a transition element, so therefore it will also be a colorless solution. Cobalt 2 plus ions will be pink in color, nickel 2 plus will be green, copper will be light blue. So these are the colors of cobalt, nickel and copper 2 plus ion solutions. Chromium 3 plus will also be green. So there are two ion solutions that will form green color solutions, chromium and nickel 2 plus ions, chromium 3 plus ions and nickel 2 plus ions. Fe2 plus ions will be light green, but still a shade of green. Manganese 2 plus will be light pink. It is almost colorless. It's a near colorless solution in the lab environment when you're observing it. Even when we are doing a practical, you will observe the same. And Fe3 plus ions will be yellowish brown in color. Fe3 plus will be yellowish brown in color. So students, the theory parts revolving around this practical, experiment number 18, is covered. Now all that we have to do is go into the lab and complete the experiment. So let's move into the lab and observe the colors of these aqueous cation solutions. GCE Advanced Level Chemistry Practical Series Experiment number 18. Identification of the colors of complex ions in aqueous medium. In this experiment, we are going to observe the different colors of the complex ions that are formed by D block elements. Now, let's move on to identifying the chemicals we will be using for this experiment. Let's identify the chemicals we will be using for this practical. We will be using chromium chloride. As you can see, the chromium salt we have here is greenish in color. So it's a dark green color solid, chromium chloride. And then we have manganese sulfate. Manganese sulfate is slightly pink in color. Please observe, students, this is not white. The manganese sulfate salt is going to be slightly pink in color. And then we have ferrous sulfate. Now, ferrous sulfate, this solid that we have here, is slightly green in color. As you can see, it is slightly green in color. And then we have ferric chloride. So as you know, iron has two oxidation states, Fe2 plus, which is ferrous, and Fe3 plus, which is ferric. So ferric ions are present here in this salt, which is ferric chloride, which is brown in color. And then we have cobalt chloride. Cobalt salts normally appear slightly red or pink. So what you have here is cobalt chloride. And then we have nickel nitrate here. Nickel nitrate is green in color. You can see the solid nickel nitrate is green in color. And then we have copper sulfate. I'm sure that all of you have come across copper sulfate in the lab. So copper sulfate, one interesting fact about copper sulfate is, copper sulfate, when it is present in its hydrated form, it appears this pale blue color. However, if you have anhydrous form of copper sulfate, it will appear white. And then finally, we have zinc sulfate. Now zinc sulfate or zinc salts are going to appear white. This is due to the fact that zinc is not a transition element. So therefore, zinc 2 plus ions, especially when they are dissolved and when zinc 2 plus ions are present in aqueous medium, they are not going to be having a color. Now, these are the chemicals we will be using for this practical. Apart from these, we will be using some test tubes and a wash bottle containing distilled water. Now, let's move on to our practical. We will first take a small amount of our chromium chloride here. As you can see, chromium chloride, we have the green color solid. And we will take a test tube and transfer a small amount of chromium chloride into our test tube. And after doing so, we can take our wash bottle and add a little bit of water and dissolve the chromium chloride solid. As you can see, when the chromium chloride solid dissolves in water, it forms a green color solution. So this green color solution contains chromium 3 plus ions. So the chromium 3 plus aqueous ions appear green in color. So in this aqueous medium, there is a complex that is formed. With one chromium 3 plus aqueous ion, there would be one chloride ligand and 5 water molecules forming coordinate bonds with the chromium 3 plus ions. The name of the formula would be penta-aqua chlorido chromium 3. Penta-aqua chlorido chromium 3 ion. Or another complex ion that can be formed here is when 2 chloride ligands are attached to the chromium ion along with 4 water ligands. So you would form at that point tetra aqua dichlorido chromium 3 ion. So these are the chemical species that are responsible for the green color observed in this test tube or in this aqueous medium. So after observing the color, if you want to very clearly see the color, we can dilute this a little bit. So we can see a very clear green color. As you can see, the green color is now very clear. Earlier, the concentration of the complex ion was too high for it to be very clearly observed. We observed a darker green color, but now when we dilute the solution, we observe a nice green color. So keep in mind, students, sometimes when you're trying to observe these colors, we will have different shades of a given color observed based on the concentration of the ions that are present in the aqueous medium. So concentration is a factor that contributes to the intensity of the color that you observe in an experiment like this. So that is one thing to keep in mind when you're doing an experiment like this. With that, let's move on to the next compound. Up next is manganese sulfate, MnSO4. So as you can see, the manganese sulfate solid is slightly pink in color. It is not white, it is slightly pink in color. So if you take a test tube and transfer a small amount of manganese sulfate into this, and then add water to it, we will be able to form an aqueous ion solution of Mn2 plus. Let's take another test tube and transfer a little bit of this solution into another test tube so that we can observe a clearer color or a clearer solution. Now this solution at a glance might appear to you as colorless, although it might appear colorless at a glance if you compare it against a white background, or if you compare it against just a colorless solution, you would note that there's a slight hue of pink. So the color of Mn2 plus aqueous ions is pink. However, observing this color in the lab would be somewhat difficult. If you have a really high concentration of Mn2 plus ions in the medium, it might appear slightly pink. However, observing this pale pink color of Mn2 plus is not that easy. So the pale pink color that you observe here is due to Mn2 plus ions forming 6 dative covalent bonds with 6 water ligands. So the complex that you have formed here is hexa aqua manganese 2 ion. Hexa aqua manganese 2 ion. Now, let's move on to our next salt that we have here. We have a ferrous salt, ferrous sulfate. As we saw earlier, the color of ferrous sulfate solid was pale green. We'll take a little bit of ferrous sulfate into a test tube. And then dissolve it with distilled water. As you dissolve the ferrous sulfate, you can observe here the formation of a pale green color aqueous solution. It's a pale green color aqueous solution. So Fe2 plus aqueous ions appear pale green in color. So the reason for this pale green color aqueous solution is the formation of a complex ion. Fe2 plus ion forms 6 dative bonds with 6 water ligands to form hexa aqua ion 2 ion. So the color that is observed here is due to the formation of hexa aqua ion 2 ion. Again, the color of Fe2 plus aqueous ion solution is going to be a pale green color. To better observe the color of Fe2 plus aqueous ion solution, we can use a white color background. As you can see, we can observe a very pale green color with a white color background. In contrast to white color background, you can very clearly see that this solution is in fact pale green in color. Now, let's move on to ferric chloride. We have here ferric chloride that has already absorbed water from the surrounding and is already starting to dissolve. So let's take a little bit of ferric chloride into a test tube like we did in the previous instances, and let's add a little bit of water. As you can see, when a lot of ferric chloride is dissolved in a little bit of water, we can observe a really nice yellow-brown color, more towards brown. This is because the concentration of Fe3 plus ions, ferric ions, are going to be high in this particular solution. So when you have a high ferric ion concentration, you are going to have a yellow-brown color observed in this aqueous medium. However, this color is more towards brown. So let's decrease the concentration and observe the yellow-brown color of a dilute solution. So for this, we'll take another test tube and transfer a small amount of ferric chloride and add a little bit of water to it. And then, as you can see, when the concentration of ferric ions or Fe3 plus ions is somewhat moderate, not extremely high, at that point you will observe the yellow-brown color of ferric or Fe3 plus aqueous ions very clearly. So this yellow-brown color of Fe3 plus aqueous ions is due to the presence of a complex ions or due to the formation of a complex ion. Fe3 plus ions form 6 dative covalent bonds with 6 water ligands to form a hexa aqua iron 3 complex ion. However, some of the water molecules that are forming, or some of the water ligands that are forming dative covalent bonds with Fe3 plus ions will undergo deprotonation to form hydroxide ions. So this color is due to Fe3 plus ions forming dative covalent bonds with 1 hydroxide ions and 5 water ligands, or sometimes you will have ferric ions with 2 hydroxide ions and 4 water ligands. In the first instance, the name that is given to the complex that is formed is penta aqua hydroxido iron 3 ion. In the second instance, where there are 2 hydroxide ligands along with 4 water ligands, the complex ion that is formed is going to be known as tetra aqua dihydroxido iron 3 ion. So these two species are the ones that are giving this yellow-brown color to our ferric or Fe3 plus ion solution. So please observe the color clearly, because we are going to be moving on to the next compound. So the next compound that we have here is cobalt chloride. Cobalt chloride, as I told you earlier, is having a red or a pink hue. And if you take a test tube, now we are transferring a small amount of cobalt chloride into a test tube. Let's dissolve it by adding a little bit of distilled water. As you can see, when we have cobalt chloride dissolved in distilled water, it will introduce cobalt 2 plus ions into the aqueous medium. As you dissolve cobalt chloride in an aqueous medium, the color that you observe is pink. You can see the pink color of cobalt 2 plus aqueous ion medium. The species responsible for this color in this cobalt 2 plus aqueous ion medium is a complex ion that is formed between cobalt 2 plus and water. Cobalt 2 plus cations will form 6 dative covalent bonds, or in other words known as coordinate bonds, with 6 water ligands, and will form hexa aqua cobalt 2 ions. So the hexa aqua cobalt 2 ions are going to appear pink in color. So this is the color of cobalt 2 plus aqueous ion solution. Now let's move on to nickel nitrate. So we have nickel nitrate here. We'll take a small test tube. Nickel nitrate solid, as you can see, is green in color, and We'll dissolve this solid by adding a little bit of water. As you can see, as the nickel nitrate solid dissolves, we are forming a solution that is green in color. So nickel 2 plus aqueous ion solutions are green in color. Just like we have explained in the previous instances, the chemical species responsible for this color. Let's take a look at the chemical species responsible for the green color in this aqueous medium. So this green color is observed due to nickel 2 plus ions forming a complex ion with 6 water ligands. So 6 water ligands will form 6 dative covalent bonds with the nickel 2 plus ion and will form hexa aqua nickel 2 ion. Hexa aqua nickel 2 ion, which is going to be green in color. Now we move on to our final colored substance, which is copper sulfate. Let's take a little bit of copper sulfate. As you can see, copper sulfate is a pale blue color solid. As I mentioned here, copper sulfate that we have here is the hydrated form, and the anhydrous copper sulfate will appear white in color. Now let's add a little bit of water to our copper sulfate solid. As you can see, when copper sulfate is dissolved in water, the color that you observe here is going to be pale blue. We observe a pale blue color. So copper 2 plus aqueous ion solutions are going to appear pale blue in color. Let's observe that color very clearly. So this pale blue color is there due to copper 2 plus ions forming 6 coordinate bonds with 6 water ligands and finally forming a hexa aqua copper 2 complex ion. Hexa aqua copper 2 ions are the reason for this pale blue color observed in copper 2 plus aqueous ion solutions. Now we finally move on to our last compound, which is zinc. So we have zinc sulfate here. Zinc sulfate solid appears white. It's a white color crystalline solid. And then if you add a little bit of water to it, you will see that this dissolves to form a colorless solution. Zinc 2 plus aqueous ions are colorless. Zinc 2 plus aqueous ions as well actually form a complex ion. With 6 water ligands, zinc 2 plus ions will form 6 dative covalent bonds, finally forming hexa aqua zinc 2 ions. However, zinc does not form a stable ion that contains any incompletely filled d orbitals. As we know, only transition metal ions will form ions that are containing incompletely filled d orbitals. So this incompletely filled d orbitals is a necessity for these ions to show a color. Since zinc does not have incompletely filled d orbitals, or zinc 2 plus doesn't have any incompletely filled d orbitals, it will not be capable of producing a colorful solution. Instead, zinc 2 plus aqueous ions are going to be colorless. With that observation, we come to the conclusion of today's experiment. Let's take a look at all of the different colors we observed today when carrying out this experiment. Now, let's take a look at the summary of this experiment. We started off with chromium chloride. So, chromium chloride was a green color solid. When dissolved in water, it produced a green color solution. So, chromium 3 plus aqueous ion solutions are green in color. And then we have manganese sulfate. Manganese sulfate was a slight pink color solid, but when you dissolved in water, you formed a very pale pink color solution. Mn2 plus aqueous ion solutions are pale pink in color. The color intensity of this pale pink or this pale pink color is very low in its color intensity. So, you will not necessarily observe this pale pink color very clearly. However, you can compare the pale pink color with a colorless solution. So, you will observe that there is a slight change in color, a slight pink color hue when it comes to the Mn2 plus aqueous ion solutions. Unfortunately, the camera might not be able to pick up this pale pink color of Mn2 plus aqueous ion solutions. However, when you are conducting the experiment in the lab, you might be able to observe it a bit more clearly. Then we have our ferrous sulfate solid, and then we dissolved the ferrous sulfate solid. Ferrous sulfate was a pale green color solid. When we dissolved it in water, we observed a pale green color solution formed. The color has slightly changed from then to now as Fe2 plus sometimes undergoes oxidation in air to form Fe3 plus. So, Fe2 plus aqueous ion solutions were green or pale green in color. Then we have ferric chloride. So, the ferric chloride solid that we obtained was brown in color, but when we dissolved a small amount of ferric chloride, we formed a yellow brown color solution. So, Fe3 plus aqueous ion solutions appear yellow brown in color. Then we have cobalt nitrate. Cobalt nitrate solid was pink red in color. When you dissolved cobalt nitrate in water, the solution that was formed was pink in color. This indicates the cobalt 2 plus aqueous ions are going to be pink in color. Then we moved on to nickel nitrate. Nickel nitrate solid was green color, and we dissolved this nickel nitrate green color solid in a small amount of water, and it produced a green color solution. Nickel 2 plus aqueous ion solutions are going to be green in color. And the final colored compound that we observed was copper sulfate. Copper sulfate solid was pale green in color. As I mentioned earlier, the anhydrous copper sulfate will appear as a white color solid, but hydrated copper sulfate will appear blue in color. So, this pale blue color copper sulfate solid, when dissolved in water, we formed a pale blue color solution. This is due to copper 2 plus aqueous ions dissolved in water. So, copper 2 plus aqueous ion solutions are going to be pale blue in color. Finally, we took zinc sulfate. Zinc sulfate was a white color solid. When dissolved in water, zinc sulfate produced a colorless solution. As mentioned earlier, zinc is not a transition metal, so therefore the aqueous ion solutions of zinc 2 plus are going to be colorless. So, this summarizes all of the different colors that we observed throughout this experiment. Now, let's move on to some questions revolving around this experiment. Students, now you have had a look at the experiment being conducted in the lab. Now we are going to be having a look at some questions revolving around the theory parts related to the experiment number 18. So let's take a look at the first question. First question says, Q is an inorganic substance. So we know Q is now an inorganic substance. It should have a cation and an anion. And then they are going to list down some experiments that will give us an idea about what the cation and what the anion would be. When it is added with dilute HCl, a gas and a blue color solution was produced. So the two most important observations is a gas being produced and the solution being blue in color. And the gas that was produced did not react with acidified potassium permanganate. So gas was not reacting with acidified potassium permanganate. So let's discuss these 2 points. So as you know, a blue color in a solution can be produced by a transition metal cation solution. Right? So this blue color could be due to the cation. This is a inorganic substance. So that means the cation would be forming this blue color solution. And the gas that was released would be due to the anion. So the cation produces the blue color solution and the anion is producing the gas when reacting with HCl. So the blue color solution can be produced when it comes to copper 2 plus aqueous cations. When it comes to copper 2 plus aqueous cations, a blue color solution can be produced. So it would be our first guess. And then we would be moving on to the next statement, which is the gas did not react with acidified potassium permanganate. Acidified potassium permanganate is an oxidizing agent, which means the gas, whatever the gas that was produced from the anion, did not get further oxidized in the presence of acidified potassium permanganate. So now, while keeping these things in mind, let's move on to the next topic. When a portion of a blue color solution, most probably the copper 2 plus ion solution, reacted with excess ammonia. So at this point, it should ring in your mind what happens when copper 2 plus ion solution, if it is in fact copper 2 plus, what happens if copper 2 plus ion solutions react with excess ammonia? It should be forming a dark blue solution. Let's see if you find this. Yes, they say a dark blue solution was formed. So in your minds at this point, you should know as soon as you see a blue color solution, it could be copper 2 plus. And they will confirm your doubt by saying that it is reacting with excess ammonia and producing a dark blue color solution. But don't forget, students, there are 2 complexes that can form dark blue color solutions with excess ammonia. For example, if you take, now let's say excess ammonia, if you take 2 things, if you take copper 2 plus ions and include excess ammonia, you can get Cu NH3 4 times 2 plus. This is dark blue in color. And then we have nickel 2 plus. If you use excess ammonia, with nickel 2 plus, you're going to get this compound or this complex ion, which is NiNH3 6 times 2 plus, which is also a dark blue color. Actually, we call it deep blue color for both of these solutions as well. Now, if they did not give you the color of the initial solution and they said when adding excess ammonia, the solution that was formed was dark blue color or deep blue color solution, that would indicate it could be copper 2 plus or nickel 2 plus, one of the two. But they have mentioned the initial solution produced was blue, which is normally observed in copper 2 plus. Nickel 2 plus solutions are green. So it can't be nickel. So at this point, you have roughly identified what the cation is. Cation is going to be, through two tests, you have identified the cation is copper. Right, so we have our doubts about that. So we will keep an eye on for copper. So there are two answers with copper. So we'll direct our attention to them. So what are the two answers? It could be either 5 or it could be 1. One of the two. So then we have to identify the anion, as well as there are certain other information that is given here. So let's pay attention to those. When another portion of a blue color solution was reacted with H2S, we are reacting it with H2S, a precipitate was formed. Now students, this is confirmation for nickel. It is confirmation for copper, not nickel. So when it comes to nickel and copper, if you remember the qualitative analysis of cation, in group 2, we observed when you react copper 2 plus ions, copper 2 plus ions are found in qualitative analysis group 2. And in the group 2, what we are doing is we are sending H2S in an acidified aqueous medium of these ions. So when the solution is acidified, if I write the equation that is taking place, if you take H2S, H2S have the following equilibria. Although H pluses are removed in two separate stages, we will, for the convenience here, we will write it like this. So H2S has the following equilibria where it releases sulfide ions. Now in an acidified medium, the H plus concentration would be higher, which would mean that the equilibrium will be going more towards the left hand side. So equilibrium position in an acidified medium will lie more towards the left hand side of this equilibrium. So when the equilibrium position shifts to the left, that would indicate the sulfide ion concentration being very low. So in the second group of qualitative analysis of cations, you will observe all of the cations that are forming precipitates in the second group only require very small concentration of sulfide ions. Even in the presence of a very small concentration of sulfide ions, cations like copper 2 plus will form copper sulfide precipitate. So copper is found on the second group. So second group indicates copper is precipitating out as copper sulfide even in very low concentrations of sulfide ions. In this question, we started off by adding dilute HCl into this inorganic substance. So therefore, the solution is already acidified. So when you send H2S, we are creating this situation where you are sending H2S in an acidified medium. So at that point, if you are producing a precipitate, it is going to be copper sulfide precipitate, because nickel is found in our qualitative analysis group of cations, or group 4, or fourth group of qualitative analysis of cations. So in this group, all of the cations that are there, nickel is found here. In this group, you would need a really high concentration of sulfide ions. So what do? You actually add ammonium hydroxide before sending H2S through the medium. So then what happens, students, when you send hydrogen sulfide in an alkaline medium? So in an alkaline medium, this H plus that is produced will be used up due to the presence of hydroxide ions. So therefore, H plus concentration will be going down. So when the H plus concentration is going down, equilibrium position of this particular equilibrium will lie more towards the right hand side. It is going to be lying more towards the right hand side, increasing the concentration of H2 sulfide ions, not decreasing it. It will be increasing the concentration of the sulfide ions. So in the group 4, we will be precipitating out different metal sulfides with a really high concentration of sulfide ions. And to bring about a really high concentration of sulfide ions, we are going to remove H plus ions by reacting it with the alkaline medium. So alkaline medium will have OH minus, which will take away H plus ions. So when this reaction is bringing down the H plus ion concentration, equilibrium will shift more towards the right hand side and will produce more and more sulfide ions. So students, nickel will not easily precipitate out with a very low concentration of sulfide ions. It will require considerably high concentrations of our sulfide ions, but copper will precipitate out even with very small concentrations of sulfide ions. So in this question, they very clearly say, that when you send H2S into this previous solution that we have formed by reacting this Q, which is an inorganic substance, with HCl, which is now this copper 2 plus ions or nickel 2 plus ions are now present in an acidic medium. So now we are still figuring out whether it's actually copper or nickel, and we can actually now confirm that it is copper, because when you send H2S in this acidified medium, only thing that can produce a precipitate is copper 2 plus. Nickel 2 plus will not be able to produce a precipitate. So therefore, definitely the cation that we have in this medium is copper 2 plus, without a doubt. So there are only two answers with those cations, first one and the fifth one. And in the first one, we have an ion which is sulfite, and in the fifth one, an ion is carbonate. So let's take a look at those two anions. So if you take sulfite, SO3 2 minus, and carbonate, which is SO3 or CO3 2 minus, and if you add HCl, or when you react it with H plus, they are producing gases. Over here, sulfite ions will produce sulfur dioxide. You can actually identify it with the very characteristic smell of sulfur dioxide. You should not be inhaling sulfur dioxide in the first place, though, because it is a very harmful gas to inhale. And then if you add H plus ions, or if you add an acid to carbonate ions, we will produce carbon dioxide. So if these are all produced as gases, and then if you further react with acidified potassium permanganate, you will convert KMnO4. Now KMnO4 is, or permanganate ion to be precise, is acting as an oxidizing agent. Sulfur dioxide actually can decolorize the permanganate ion and form Mn2 plus. So the color of potassium permanganate, which is purple, will be colorless. Mn2 plus, as I mentioned earlier, is pale pink in color. However, it is not going to be very observable, so it appears colorless. Apart from that, it will form sulfate ions. So sulfate ions are also colorless. So sulfur dioxide will get oxidized to sulfate. Sulfur dioxide has a +4 oxidation state on sulfur. When it comes to sulfate ions, it has a +6 oxidation sulfur. So sulfur dioxide can get oxidized to sulfate, where potassium permanganate or permanganate ions get reduced to Mn2+. So you will observe a color change. So the purple color here will become near colorless. So we'll write colorless here. So keep in mind, originally it is supposed to be pale pink, but this pale pink is not going to be observable due to lack of its color intensity. It is going to be appearing colorless. However, if you send carbon dioxide, of course, there won't be a reaction. Carbon dioxide will not be further oxidized with the help of acidified potassium permanganate. So therefore, you will not see a reaction there. So what is the anion then? At this point, you have figured out what the anion is. So you have to disregard sulfur dioxide being formed, because if you use the sulfite anion, you will produce sulfur dioxide gas, but sulfur dioxide gas can decolorize acidified potassium permanganate. But it says in the question that acidified potassium permanganate was not decolorized. There was no reaction. So at this point, the answer would be copper carbonate. So the answer would be copper carbonate. This is your answer. Answer would be copper carbonate. Now let's move on to the second question. In the second question, they are saying D is an inorganic substance. Again, it is an inorganic substance. We'll have an anion and a cation. And when D is reacted with sulfuric acid, a brown color gas, we know a few brown color gases, right? A brown color gas and a colorful solution was formed. When a portion of the colorful solution was reacted with excess ammonia, a dark blue solution was formed. So excess ammonia produces a dark blue solution. Earlier on as well, in the previous question, we discussed which cations form a dark blue solution with excess ammonia: copper and nickel. And then when another portion of colorful solution was reacted with H2S, a precipitate was formed. Identify D. So now students, again a similar question to the question we looked at earlier. So there's reactant or inorganic substance D. This would mean this is an ionic substance which contains a cation and an anion. And when you react it with H2SO4, it produced a brown color gas. And a brown color gas that we currently are aware of, there are two brown color gases. We can talk about bromine gas as well as NO2, nitrogen dioxide. But bromine will not be formed when an anion is reacting with sulfuric acid. So therefore, bromine is out of the question. Bromine cannot be formed by reacting an anion with sulfuric acid. So therefore, the only option that we have here is NO2. So the brown color gas would be NO2. And when it comes to NO2, they say a portion of the colorful solution was reacted with excess ammonia. So they are not, in this case, they are not directly letting us know what the color of the solution was, because the color of the solution, depending on that, we can very easily find out whether it is copper or nickel. So the color of the solution is kept out of this question. When it comes to the previous question also, we learned that there are two cations that will form a dark blue solution with excess ammonia. Those were copper 2 plus and nickel 2 plus. Copper 2 plus was actually found in the second group of qualitative analysis of cations. And when it comes to nickel 2 plus, it is found on the fourth group. Now students, when it comes to the second group, we know second group will produce a precipitate when H2S is sent in alkaline or in acidic medium. When H2S is sent in acidic medium. And when it comes to the fourth group, we need to send hydrogen sulfide in alkaline medium for them to produce a precipitate. So in alkaline medium, the sulfide ion concentration is extremely high, and then only cations like nickel 2 plus will produce precipitates. But when it comes to the second group, the concentration of sulfide ions is quite low. So even in low concentrations of sulfide ions, copper can produce a precipitate. So in this case, we have the colorful solution which is already acidified, and we are sending H2S through it, so it is producing a precipitate. So what does this mean? This indicates we are talking about copper. This indicates that we are talking about copper. So all of these other nickel related answers are not considered. Or even cadmium. Cadmium 2 plus ions are colorless, right? Cadmium is the element that is found directly below zinc. So zinc 2 plus, cadmium 2 plus, mercury 2 plus, these ions are forming colorless solutions in aqueous medium. So therefore, cadmium is not going to be considered. Apart from that, so we have nitrate and nitrite. So which one will produce the brown color gas? So the brown color gas is produced. We'll take a look at the reaction first. When you take nitrite ions, so the answer was between nitrite ions and nitrate ions. So if you react nitrite ions with sulfuric acid H2SO4 and nitrate ions with H2SO4, you're going to produce, when it comes to nitrite ions, you will produce NO2 gas. This gas is going to be a red-brown color gas. We'll call it a brown color gas, which is produced. Again, you should not be inhaling it. And when it comes to adding sulfuric acid to nitrate ions, there won't be a reaction. So therefore, we can disregard this answer as well, and our answer, correct answer, is going to be number 2, copper nitrite. Copper nitrite will be your answer. And now let's move on to the next slide. In the next question, they're asking what is the correct formula of pentamine hydroxo cobalt. So pentamine hydroxido cobalt to cobalt 3 nitrate. So in this question, they are saying there are 5 amine groups. So there are 5 amine groups, and one hydroxido suggests that there's one OH minus group. Instead of calling them groups, a better way to address them is ligands. So we have 5 amine ligands along with one hydroxide ligand. And the cation that are connected to these ligands are going to be cobalt 3 plus. So oxidation number is given 3 plus is the oxidation number of cobalt that we have here. And how do we now organize these ligands in this complex? So when it comes to writing the name of a complex like this, we have to keep in mind we are following the alphabetical order. And at the same time, when it comes to organizing the ligands inside the formula as well, we will be following the alphabetical order. So you will have nitrogen appearing before oxygen, right? Not nitrogen, actually N appearing before oxygen. So therefore, when you are writing this, you first indicate the cation, cobalt, and then followed by the ligand that comes first in the alphabetical order. So according to the alphabetical order, N comes first before oxygen. So you should have NH3. How many of amine ligands are there? There are 5 of them, so we'll indicate it outside of the bracket. And then we have one hydroxide ligand, so it is going to be followed by the amine ligand. And then we can think of the charge of this complex. What is the overall charge of this complex? So if you take a look at the overall charges, I will erase these now. If you take a look at the overall charges, you'll be clearly able to observe the cobalt that we have here has a charge of +3. What about ammonia? There are no charges. And when it comes to our hydroxide group, there's one negative charge. So when you combine all of these together, the overall charge would be +2. So you're going to see a 2+ charge over here. And then they are saying pentaamine hydroxide cobalt nitrate. So the nitrate ion is there connected to this complex ion. So imagine a nitrate ion being here. A nitrate ion has a charge of -1, but the overall charge of this complex cation is +2. So to neutralize that charge, you would require 2 of these. So because of that, when you're writing the formula, you have to have this cation connected with NO3 twice. So let's take a look at the answers, whether we have those answers here. The very first one, you see cobalt and then hydroxide ion, and then you have amine ligands. So sometimes in certain years of these questions, you will find the order of the ligands being mixed up, but still, if the charges and the entire formula as a whole is correct, sometimes you have to select that as the most appropriate answer, because if all of the other answers are incorrect, just because the ligands are mixed up, you will not be able to consider it to be the wrong answer, because all the other wrong answers will be having wrong charges or wrong formulas entirely. So then you can't go for those answers. But in this situation, you can see the third answer is exactly the answer that we wanted to have. So you have this formula where there are 5 amine groups along with 1 hydroxide, and then there are 2 nitrate groups present right next to the complex cation. So therefore, the answer would be 3. Answer would be 3. So in this particular question, we have not mixed the 2 ions, but if the 2 ions are mixed in certain questions, always try and select the most appropriate, most accurate answer. Now, when you are moving on to the next question, this question is a structured question. A white solid A contains 1 cation and 1 anion. So it's an inorganic substance containing a cation and an anion. When water is added slowly, the solid turns blue and then dissolves to form a blue solution, B. So students, let's move on to this area. So we have a solid A. When added with when added with water, drop by drop, they're adding H2O. This white color solid turns into a blue color solid. So, have you ever observed this situation before? Yes, we did speak about this in the beginning of this practical. Now, in your lab, we told that copper sulfate is how you normally observe your copper 2 plus ions. So, copper sulfate is going to be majority of the time present as the hydrated form in the lab, which is CuSO4 5H2O. This is one of the hydrated forms of copper sulfate. And the anhydrous form, that means water-free form of copper sulfate, is referred to as the anhydrous form of copper sulfate. Anhydrous copper sulfate solid is going to be white in color, and the hydrated form of copper sulfate is going to be blue in color. So, by just looking at the very first part of the question, you can have an idea that this could be copper sulfate. And what they have originally taken as A could be anhydrous copper sulfate, and what they originally taken as B could be hydrated copper sulfate. And then they say they fully dissolve this in enough and more water to form a blue color solution. So what will be your blue color solution? What can be your blue color solution? It will be copper sulfate solution, or Cu2 plus. Aqueous solutions were blue in color. We just looked at it today. And what is the complex that is formed? Hexaqua copper 2 ions. Hexaqua copper 2 ions. So this is the species responsible for the blue color. And now they're asking you, when the solution barium chloride is added, right? So after identifying the cation, we can move on to that. When the solution barium chloride is added to an acidified portion of solution B, so it is acidified, a white precipitate was formed. So this is basically copper sulfate that we have. So to copper sulfate, we are adding barium chloride. Give the formula of the anion in B. So we do know the entire formula, which is copper sulfate, or in this case, they further confirm the anion is sulfate by adding barium chloride. Why? Because we know when barium ions, that is another area that we are going to explore. When barium ions, when you have barium chloride added to the solution, it forms barium 2 plus aqueous ions along with chloride aqueous ions. So barium 2 plus ions, when they come into contact with sulfate aqueous ions, so these aqueous ions, when they are in contact with one another, they will form a precipitate. Barium sulfate is going to be a white color precipitate. So the addition of barium chloride bringing us a white color precipitate confirms our doubts about the anion, because anion, we originally thought the entire compound that we have here is copper sulfate. So copper sulfate, of course, has an anion sulfate. So now addition of barium chloride confirms the presence of the sulfate ion, and thereby the compound could be copper sulfate. So the formula of the anion is going to be sulfate. So we can just write formula is SO4 2 minus. Name a suitable acid for acidifying the solution in B for this particular test. So students, without saying or mentioning anything about this, you should know if you are using barium chloride to identify the presence of sulfate, you should not be using acid that contains sulfate ions. So you cannot use, these are the things that you cannot use. You cannot use sulfuric acid because sulfuric acid will bring in sulfate ions. So you cannot use sulfuric acid. But any other acid like hydrochloric acid or nitric acid can be used. So these are the two acids that we can use for this acidification process. Then in the A part, they are asking you the formula. You can write it here. The question solutions, you can write them here very clearly. SO4 2 minus, and in this case it is going to be HCl and HNO3. And the third part or B part of the question, they are saying an aqueous ammonia is added to another portion of solution B. A blue precipitate was formed and more aqueous ammonia is added. This precipitate dissolves to form a deep blue solution. This is indicative of the behavior of copper 2 plus ions. Copper 2 plus ions will produce a blue color precipitate in the presence of hydroxide ions. However, if you add excess ammonia, these hydroxide ions will dissolve or this precipitate will dissolve in excess ammonia and will form a blue color, dark blue color or deep blue color solution. So identify by name or by formula what the blue precipitate is. And in the second question, give the formula of the ion responsible for the deep blue solution by C. So first of all, let's answer the first question. Identify name or by formula the blue precipitate. So the blue color solution that we have in this question is copper 2 plus aqueous solution. So this is copper 2 plus aqueous solution. When you react it with ammonium hydroxide brings in OH minus ions to the medium. So this will produce copper hydroxide, which is a pale blue color precipitate. And then when you're talking about, so what is the precipitate that we are forming here? The precipitate that we want is this. The precipitate that we're talking about, blue color precipitate, is copper hydroxide. And in the next question, they're asking you, give the formula of the ion responsible for the deep blue solution. So when you are adding excess ammonia, now we are starting with copper hydroxide. If you are taking the copper hydroxide solid and reacting it with excess ammonia, if you are reacting it with excess ammonia, you will be forming this complex. Copper will form 4 coordination bonds with 4 ammonia ligands and will form this complex. Tetra amine, AMMINE, copper 2 ions. Tetraamine copper 2 ions are the ions that are formed. Give the formula of the ion responsible for the deep blue solution. This will be the formula of the ion responsible for the solution. So if you have written this, you don't have to write the equation. If you have written this formula, you will obtain marks allocated for a question like this. In this question, they are asking you to give the formula of complex ion which gives the blue color to the solution B. Now, solution B was obtained by solid A being dissolved in water, right? So when you dissolve a lot of A in distilled water, we observed a blue color solution, and this was due to the presence of copper 2 plus ions. So when copper 2 plus ions come into contact with water ligands, so this is the cation or central cation, and these are the water ligands. When they come into contact with one another, what is the formula of the complex that is formed? So 6 water ligands come into contact with the copper 2 plus cation and form 6 coordination bonds or dative covalent bonds to form this ion. This is the ion responsible for the pale blue color solution that is formed. We learned about this in the theory parts as well as the practical today. And then the D part of the question, they're asking you to give the formula of the white solid A. So in the beginning of the question itself, we discussed the white solid that we had was anhydrous copper sulfate. So it's only anhydrous that turns into a blue color solid when exposed to water vapor or a little bit of water. So if you take water and you expose it to a little bit of water vapor, this anhydrous white color copper sulfate solid will turn into a blue color hydrated solid. So anhydrous copper sulfate is CuSO4 solid. In addition, when you add water to it, it will turn into CuSO4.5H2O. This is also in the solid form. This will be blue in color. But the anhydrous form is going to be white in color. So what is the white solid A? A is this. This is your A. The A solid is copper sulfate anhydrous solid. So now students, today we have discussed a few questions revolving around the theory parts of experiment 18 as well. So from the beginning, we looked at the theory revolving around different transition metal cations. Basically, we looked at all of the different colors of 3D transition metal cation aqueous solutions. And then we moved on to our lab and we observed all of these colors. And at that point, we made very important observations, especially when it comes to manganese. Although in text, we say the Mn2 plus aqueous ions or manganese 2 plus aqueous ions are going to be pale pink in color. Most of the time in the lab environment, we observe it to be near colorless. But when it comes to your exams, you have to mention the color of Mn2 plus aqueous solutions are going to be pale pink in color. And after that, after observing all of these reactions in the lab, we came here and we had a look at some questions revolving around the experiment 18 and the theory parts of experiment 18. I hope you have obtained a significant amount of information about these cations and their colors, and I hope this will be helpful for you in your exams. We'll meet again in the next experiment.